Troubleshooting Basics for Equipment in Semiconductor Industry. Welcome to this training on troubleshooting basics for equipment in the semiconductor industry. This course is designed to provide essential knowledge, practical methods, and proven best practices for identifying and resolving equipment issues efficiently. Whether you're new to the field or have years of experience, mastering troubleshooting is key to maintaining uptime, ensuring safety, and supporting process control. We'll cover core troubleshooting concepts, including systematic diagnosis techniques, routine and predictive maintenance strategies, and performance optimization. These areas are critical to reducing downtime and improving productivity across the fab. Our content is tailored for a general audience, including operators, technicians, engineers, and managers, ensuring that every role can understand and contribute to effective problem solving. Throughout the training, we'll explore real-world examples, highlight tools and approaches, and share insights that support consistent and repeatable troubleshooting success. Critical tools in modern chip manufacturing. Semiconductor chip manufacturing relies on several critical process tools, each playing a unique and essential role in transforming raw silicon wafers into functional devices. Lithography is the first key step, responsible for pattern creation. It uses light to transfer intricate circuit patterns onto the wafer, requiring critical precision to maintain design integrity. Next is etching, which removes selected material based on the lithography pattern. This process demands precise control to achieve accurate feature shapes and depths. Deposition follows, where thin material layers are built up to form circuit structures. A uniform coating is vital here to ensure performance and yield. Inspection is integrated throughout, acting as a quality control gate. Its primary role is defect detection, allowing engineers to catch problems early. Together, these tools form a tightly connected process flow, from silicon wafer to lithography, etching, deposition, and ultimately to the final chip. Consequences of equipment. Downtime in semiconductor manufacturing. In semiconductor manufacturing, equipment downtime is one of the most serious issues a fab can face. When critical tools stop functioning, production halts, leading to immediate revenue loss. These interruptions can delay product deliveries, damage customer trust, and disrupt the tightly scheduled manufacturing flow. The cost impact of downtime is staggering, often exceeding $1 million per hour. Lost wafers must be scrapped, increasing material waste, while rework costs add even more financial strain. In high-volume fabs, even short disruptions can affect thousands of units. That's why quick resolution is vital. The goal is to minimize operational and financial impact, restore production as fast as possible, and implement solutions that prevent future occurrences. Effective troubleshooting processes are the backbone of this effort, enabling faster diagnosis, smarter repair decisions, and sustainable fixes that keep the line moving and product quality intact. Systematic approach to problem resolution. A universal troubleshooting methodology is essential for effective problem solving in semiconductor equipment. This process begins with defining the problem, clearly identifying the issue without assumptions. Next, gather relevant information, including equipment logs, operator observations, and sensor data. The third step is to analyze symptoms, connecting the evidence to possible causes. Then, test potential solutions carefully, using controlled methods. Finally, verify that the resolution worked and that the issue is truly fixed. This systematic approach ensures each step is logical, documented, and free from premature conclusions. A data-driven mindset supports this, collecting objective evidence, using calibrated tools, and confirming findings with multiple sources. At the core is a root cause focus. Don't just treat symptoms, ask why multiple times to uncover the deeper issue and prevent recurrence. Throughout, prioritize speed, accuracy, and safety. Documenting the process ensures future reference, team learning, and traceability for audits or repeat events. Essential procedures. Before equipment troubleshooting. Before any troubleshooting begins, safety must always come first. Equipment can be replaced, people cannot. Never start work without following proper safety protocols. The first step is a complete equipment shutdown. This means powering down the system fully to eliminate any active hazards. Next is lockout-tagout, which ensures all energy sources are securely isolated and labeled, protecting against accidental startup. After that, perform PPE verification. Confirm that the required personal protective equipment is on hand and in use. Finally, clear the work area of unnecessary items and people to maintain a safe and organized environment. Required PPE typically includes a safety helmet, glasses, gloves, and shoes for protection against physical hazards. ESD clothing is critical for static-sensitive environments, and a gas monitor may be necessary for chemical detection. Each of these steps helps create a safe, compliant, and prepared environment for effective troubleshooting. Essential procedures. Before equipment troubleshooting. Before troubleshooting any equipment, it's critical to follow the lockout, tagout, or LOTO process to ensure personal safety and equipment integrity. Begin with shutdown. Turn off the equipment following its standard shutdown sequence. Next, isolate all energy sources, including electrical, hydraulic, pneumatic, and thermal, to eliminate potential hazards. Then, physically lock those energy sources using lockout devices. Tag the lockout points with clear warning labels that display the technician's name and contact information. Finally, verify that all energy has been removed by testing for zero energy state before beginning work. Alongside the LOTO process, ensure readiness for emergencies. Know how to reach your emergency contact, usually 911 or facility security. Be aware of fire safety protocols, including fire extinguisher locations. Locate first aid kits and trained responders. Lastly, understand evacuation procedures, exit routes, and assembly points in case of a critical event. Essential equipment for semiconductor troubleshooting. Troubleshooting semiconductor equipment requires a combination of electrical, software, and visual diagnostic tools. Under electronic measurement, a digital multimeter is essential. It measures voltage, current, and resistance, helping to quickly identify circuit failures. It also performs continuity testing to check for broken connections and diode testing to assess directionality and junction integrity. An oscilloscope is used for waveform analysis, timing verification, and checking signal quality, especially critical in high-speed digital or analog circuits, where timing and noise are major concerns. For software diagnostics, system monitors provide real-time performance tracking, helping to flag bottlenecks or abnormal behavior. They also allow for error log analysis and trend tracking over time. Debug tools are equally important. They let engineers step through code execution, inspect memory states, and verify logic states, which is crucial for software-controlled equipment. Lastly, visual inspection includes microscopy, useful for checking component placement, solder joint quality, and identifying cracks. Thermal imaging reveals hot spots, heat distribution issues, and potential overheating, often the hidden root cause of intermittent failures. Each of these tools plays a vital role in diagnosing and resolving equipment issues efficiently and accurately. Systematic diagnostic approach. A structured diagnostic approach is critical for efficient and accurate semiconductor troubleshooting. The process begins with visual inspection, which often reveals obvious issues like loose connectors, burn marks, or component damage. Afterward, proceed to basic electrical tests, using tools like multimeters to check for voltage, current, resistance, or continuity issues. Once the hardware appears stable, shift to software analysis. This includes checking system performance logs, running diagnostics, and identifying error codes. If necessary, move on to advanced signal analysis using oscilloscopes or logic analyzers to evaluate timing, signal integrity, and communication protocols. Finally, always verify your findings by confirming the system behaves as expected after interventions. Throughout this process, 4 key principles enhance success. Precision ensures you select tools that match the required accuracy. Speed balances real-time and offline diagnostics to avoid downtime. Safety emphasizes non-invasive testing when possible to reduce risks. And data collection allows for future analysis and process improvement. Following this systematic flow prevents guesswork, reduces troubleshooting time, and increases the likelihood of long-term equipment reliability. Typical problems in semiconductor manufacturing. Semiconductor manufacturing environments commonly experience both electrical and mechanical problems, each with distinct impacts. Electrical failures are classified as high impact due to their potential to abruptly halt operations. These include power supply fluctuations, which can destabilize sensitive systems, circuit breaker trips, indicating overloads or faults, signal interference, which can corrupt data or disrupt communication, and component overheating, which often leads to permanent damage. These issues result in serious consequences such as system downtime, high repair costs, and safety risks due to potential electric shock or fire hazards. The occurrence frequency for electrical failures is around 35%. In contrast, mechanical issues are medium in impact but still significant. These usually involve unusual vibrations or noise, often early indicators of trouble. Belt and bearing wear, which can degrade performance over time. Alignment problems that affect precision. And lubrication failure, which can cause friction and wear. These problems lead to gradual degradation, quality impact, and increased maintenance cost. Mechanical issues occur slightly less frequently, at about 28%, but they still require regular monitoring and preventive maintenance. Understanding both categories is essential for ensuring reliable, efficient semiconductor production. Typical problems in semiconductor manufacturing. Two more categories of common issues in semiconductor manufacturing include software glitches and environmental conditions. Software glitches, which account for 22% of occurrences, involve code or control-related problems. These can result in system freezes or crashes, which halt production unexpectedly. Another concern is incorrect process control, where the software fails to execute proper sequencing or timing. Data corruption and communication errors between systems or sensors can also occur, leading to poor decision-making by automated systems. The impact of software issues is variable, depending on the severity and system redundancy, but often involves quick recovery, process impact, or update cost. Environmental factors represent 15% of issues and are considered preventable with proper controls. These include temperature variations and humidity changes, which affect process stability and material properties. Contamination buildup, particularly from particles or gases, can ruin wafers or interfere with equipment. Air quality issues may lead to long-term degradation. While these problems are less frequent, they can lead to quality drift, requiring constant monitoring and proactive prevention efforts. Managing software integrity and facility conditions is crucial for ensuring both process stability and product quality in semiconductor manufacturing. Typical problems in semiconductor manufacturing. In semiconductor manufacturing, identifying and categorizing issues quickly is essential to maintaining productivity and safety. Problems typically fall into 4 critical recognition patterns. First, immediate problems are the most severe. These include safety hazards or situations that require the facility to completely shut down operations. These demand urgent intervention to protect people and equipment. Second, urgent issues may not cause shutdowns, but result in significant performance drops or quality problems. These need fast resolution to prevent yield loss or customer impact. Third, scheduled issues involve gradual wear and predictable failures. These problems often show early warning signs and can be addressed through planned maintenance. Finally, preventive issues are recognized before any failure occurs. These may stem from environmental changes or ongoing maintenance routines. Identifying these patterns allows for efficient, proactive problem management throughout semiconductor production. Systematic methods for root cause discovery. To address failures effectively in semiconductor manufacturing, Systematic methods for root cause discovery are essential. One foundational method is observation, which relies on visual and sensory techniques. This includes recognizing visual inspection patterns, detecting abnormal sounds or vibrations, noting temperature fluctuations, and identifying environmental changes. These are frontline indicators that something has gone wrong. Next is data analysis, which uses quantitative approaches such as trend analysis, statistical correlation, performance metrics, and historical comparisons. These techniques help uncover patterns that may not be visible through simple observation. For deeper investigations, root cause analysis tools are employed. This includes the 5 whys methodology, fishbone diagrams, fault tree analysis, and the FMEA approach, each helping teams to drill down to the underlying issue. Finally, decision trees provide a structured, logical path through binary decisions, symptom prioritization, guided troubleshooting, and systematic elimination, ensuring a disciplined, repeatable problem-solving process. Systematic problem identification flow. Effective root cause discovery relies on a structured flow for identifying and solving problems. This process begins with the first step, gathering information. This includes documenting symptoms and reviewing system history to understand the context. Next, in the analyze stage, patterns are examined, trends are identified, and correlations between events are noted. This helps establish meaningful connections in the data. The third step is to hypothesize. Here, teams propose possible root causes, supported by theory and initial testing, to evaluate the likelihood of each possibility. Finally, in the verify phase, the solution is tested and validated through confirmation techniques. Supporting this flow are 5 core principles: maintaining a systematic approach, documenting every finding, using multi-source techniques, prioritizing the most likely causes first, and validating the hypothesis. A severity assessment, ranging from low to critical, guides how urgently a solution must be found and implemented. 5-step problem resolution methodology. Troubleshooting in semiconductor manufacturing demands a structured approach to isolate, understand, and resolve issues effectively. The 5-step problem resolution methodology provides a logical framework known as the troubleshooting progress flow. It begins with a define phase, where the problem is clearly identified, including boundaries, symptoms, and impact. Clarity here is essential to avoid misdiagnosis later. In the analyze phase, data is collected and reviewed to detect any underlying trends or inconsistencies. This is where insights start to form. Next, the hypothesize phase allows teams to propose potential causes based on the analysis. These hypotheses are not assumptions. They are targeted theories ready to be tested. In the test phase, controlled experiments or simulations are conducted to confirm which hypothesis holds true. Finally, the implement phase involves putting the verified solution into practice, monitoring outcomes, and ensuring the problem is resolved with minimal disruption to operations. Troubleshooting progress flow. The troubleshooting progress flow outlines a clear 5-step problem resolution methodology to guide teams from issue identification to successful resolution. Step 1 is define, where the team documents symptoms, assesses the impact, sets boundaries around the issue, and establishes timeline goals. This stage is essential for crafting a clear and focused problem statement. Step 2 is analyze, involving the collection and review of relevant data. It includes evaluating historical information, identifying patterns, checking for correlations, and inspecting environmental factors. These insights guide the direction of further troubleshooting. Step 3, hypothesize, requires ranking potential causes, building theory, planning test approaches, and performing risk assessment. This helps prioritize the most likely scenarios. In Step 4, test, teams conduct controlled tests, document results, validate or disprove the theory, and explore alternatives if needed. Finally, Step 5 is implement, executing the chosen solution, monitoring its performance, verifying the fix, and updating documentation to close the loop. 5-step problem resolution methodology. Effective problem resolution in any technical or operational environment requires a structured approach supported by key success factors. This methodology includes 5 essential support practices that help ensure successful problem solving. First, document every step. Capturing actions, observations, and data in real time builds a reliable record and improves traceability for future troubleshooting and audits. Second, verify each stage. After completing a step, confirm that expected outcomes are met before proceeding. This prevents cascading errors. Third, communicate with the team. Open, consistent communication ensures alignment and brings diverse insights into the resolution process. Fourth, iterate when needed. Not all problems are solved on the first try. Be prepared to revisit earlier steps, test again, and refine your solution. Finally, learn continuously. Every issue is a learning opportunity. Reflect on root causes, team dynamics, and tools used to improve future responses. These 5 success factors enable disciplined, adaptive, and collaborative problem solving. Proactive strategies to minimize equipment failures. Minimizing equipment failures starts with implementing proactive maintenance strategies that reduce downtime and extend equipment life. The preventive approach is time-based and includes regular inspections, scheduled component replacements, calibration cycles, and routine cleaning protocols. These actions are typically conducted as daily tasks to maintain reliability. The predictive strategy is data-driven and leverages sensor monitoring, trend analysis, and AI algorithms to anticipate failures before they occur. This method involves weekly analysis of real-time data to identify patterns that signal early-stage issues. The condition-based approach uses performance thresholds and real-time monitoring systems to trigger alerts and corrective actions when equipment begins to degrade. These are reviewed on a monthly basis. Lastly, proactive optimization focuses on continuous improvement through process enhancements, equipment upgrades, employee training, and sharing of best practices across teams. This is part of long-term, yearly planning to raise overall system resilience and operational excellence. Maintenance schedule timeline. A well-structured maintenance schedule is crucial for minimizing equipment failures and maximizing return on investment. The timeline begins with daily tasks, such as visual checks, basic cleaning, and log readings. These actions help catch minor issues early and ensure smooth operations. Next, on a weekly basis, teams conduct system diagnostics, perform lubrication, and change filters. These steps support ongoing equipment health and prevent intermediate failures. Monthly maintenance involves more detailed efforts like deep cleaning, calibration checks, and wear assessments. These tasks help catch gradual degradation before it leads to downtime. Yearly efforts include major overhauls, component upgrades, and full system optimization, aiming for long-term reliability. The benefits are clear: up to 75% downtime reduction, 60% cost savings, 40% equipment life extension, and 85% productivity improvement. As shown in the ROI scale, investment in this approach leads from initial costs to break-even and ultimately to sustained savings and optimization. Excellence in semiconductor equipment troubleshooting. Achieving excellence in semiconductor equipment, troubleshooting requires a blend of structure, precision, teamwork, and continuous improvement. A systematic methodology is the core foundation. This involves following a structured process, documenting every step, verifying results before moving forward, and using decision trees to evaluate root causes and outcomes logically. Next, documentation excellence is vital. Real-time logging helps track the process as it unfolds, while root cause analysis identifies the origin of issues. Solution validation ensures the fix works as intended, and knowledge sharing allows others to benefit from the resolution. Strong team communication is key. Clear escalation paths ensure timely support, while regular status updates and cross-team collaboration foster alignment. Sharing lessons learned builds organizational resilience. Finally, focus on continuous improvement drives growth. This includes regular skill updates, optimizing existing processes, adopting new technologies, and evolving best practices over time. Together, these 4 pillars support world-class troubleshooting performance. Key takeaways for excellence in semiconductor equipment troubleshooting. Excellence in troubleshooting begins with 4 essential principles. Safety first, ensuring no action compromises health or equipment. Think systematically, meaning each decision follows a structured methodology. Data-driven decisions, which prioritize facts and analysis over assumptions. And a preventive mindset, which anticipates problems before they escalate. Together, these principles drive outcomes such as 95% efficiency, 90% reliability, 85% quality, and 80% innovation. On the right, the troubleshooting journey illustrates growth from beginner to expert. The key message is, every expert started as a beginner. Mastering the basics creates a solid foundation for excellence in semiconductor manufacturing. To advance, follow these next steps to mastery. First, apply immediately. Use these principles in your next session. Second, build your toolkit by developing strong documentation and diagnostics. Third, share and learn by collaborating and contributing to team knowledge. Remember, the best troubleshooters excel through practice, patience, and continuous learning.